Okay, last Friday, I kind of stopped myself to explain some details on the course, the content. I'm going to slightly revisit and explain to you a little bit better. That's what I'm going to do. Because this is kind of the very straight, if you look at carefully, very straightforward, the theory, but still a little bit foggy in there. So if you can really catch the essence of it, then computational procedures, when you face that procedure, then it's a little bit not clear. If it's not clear, you can't get to the destination. When you just leave the runway, you have to know where you're heading. Otherwise, we got a slight problem. So starting with PF and this integration form, as we know. I'm gonna restart quickly from the U space. We transformed from X space to U space to simplify the procedure to compute the PF. And this is a phi U. The simplest form is something like this. I think we have done that like that, right? In the U space. So we're going to work on the U space to get the final result, which is probability of failure, or the reliability. You can do the same thing. So here, then GU, same thing. Then over here, this is the phi is what we did was N, and the phi U still this. As you look at this, this is from here to here, there is assumption which is independent each other. It's exclusively each other. Event is what we assumed here. And here, the phi so phi U, just this portion, that portion, I'm going to rewrite over here. Others are simply carry over all the way through. So here, I start to screw up again. I really hope not today. I'm going to start from here to match the same equation set. This is equation set 7-9. This is equation set 7-9 in the U space. And this is equal to exactly that. I is equal to 1 through n phi U I, because U has n different entry, the random variable, for n-dimensional, which is equal to the pi I is equal to 1 through n, and I put this bracket here, 2 pi exponential minus 1/2 ui squared, and closed. Up to here is not even last Friday, even just before we got that point, but I'm going to be just rewrite the portion to make the whole steps very clear. So here, this portion, I'm going to expand a little bit here. Is phi u ui is equal to 1 over 2 pi n power, because pi is nothing but the multiplication of the entry, is exp. I can write this is a very important equation, kind of midway equations, because it's repeat the ith entry, ith random variable all the way through. So for the exponential function, you can add the exponent. So if you keep adding it, then you can drop this. That's what you have there. ui squared. And of course, I wrote this as a final reminder, is equal to, this is again, you can write I is equal to 1 through n, 1 over square root of 2 pi exp, same thing, minus half ui squared. Then all this has to be in integration integration du2 all the way through du, and that's, we have done that last Friday. But the good thing to work on the U space, let's say this is U1, U2, okay, then it's all, you can draw contour as a concentric circles, right? Concentric circles probability density function for each random variable in the U space is a normal, standard normal density function whose mean is equal to 0, and standard deviation is equal to 1, right? That's what the beauty for the standard normal distribution, and projection down on the U1, U2 space is just like this. Then you can have, if this is a density axis, then you can have the volume grows up to here, down to goes down, and someplace you can have the surface, which is called failure surface, right? So this is like is equal to 0. This region is GU less than equal less than 0. And the other side is GU. Safe region, failure region. This is performance function or limit state function, or right at the failure surface. So talking a little bit ahead of the time here, we are looking at the so-called MP point, which is MPP point, which is the most probable point, is what we are looking for, or this is we specifically called expansion point for Taylor series. What does it mean, the MPP point or the U star point? We cast into the optimization problem. So if I draw the line here, from here to here, this is U star point, and the distance from here to here is known, which is, I just review the stuff which I talked last Friday. And this is a tangent. Beauty is this is a tangent to this U, the GU equal to 0. And you can say that tangent means when I pick this as the center of the circle with the distance of U star, distance of the U star also defined as a beta, which is called the reliability index. This is reliability index. I can draw the circle here. I center here. I can draw the circle. Okay. So U star absolute is known. The distance is equal to the beta. So this is a scalar quantity, is the beta, because this is a known. So, you know, it has a story behind. So we did step 2. Step 1, this portion belonged to step 1. For the step 2, step 1, we were looking at how to simplify the integrand, which is a probability density function. So this time we're going to look at the integration boundary. Integration boundary is GU. How to simplify the integration boundary, because we have to work on the U space. So then we reduce the G using the Taylor series, and by taking the first 2 terms, which means only the linear portion. So here is a G U star, and to signify we are working on the linear portion, so approximate as L. This is just symbol saying we're going to deal with the linear portions, not including the square terms. So this is equal to GU star, expansion point, or most probable point is what this point is. Second term is gradient GU star and U minus U star transpose. If it's one-dimensional, it's a straight multiplication. But this is n-dimensional, the multiplication of n-dimensional vector. So you have to have a second term transpose, so you can multiply row by column. Then you can have a total, the summation. If you carry out the expansion, it's going to be the summation. And that's what we did. Then of course here expression for delta G U star has n-dimensional term. If it's only plane, it's ij. If it's a three-dimensional ijk, you can expand it. So what we use is delta simply by comma n different terms you have to do. So this is a del G U del U1. So this is evaluated at the expansion point U star. Okay. So it's a del G U del U2 all the way through del G U del UN. N-dimensional term. Because U, just as a reminder, U is UI, I is equal to 1, 2, all the way through N. Okay. So then as we discussed last Friday also, this is a cutting plane. This is, you remember this? This is the probability density function, and cut right at the G is equal to 0. And look at what, this what page? Page 8? What page number? The pictures I'm not that good at picking. Page 10, I think, is 4.6. 4.6. The idea is approximation to deal. This is just a lifted up portion. This portion is the highest, the probability density point, right? So whole idea is to approximate the point, which is this is G. U is equal to 0. Right at that point is, of course, U dot point, right? So to maximize, pick out the U star point right at maximum probability density point to define the GU equal to 0. That's the whole idea. As approximation, because afterward, this point is really going down pretty fast. So as approximation, we're going to pick out the U star or MPP point where the maximum peak in the probability density function occurs right at the failure surface. Okay, that's all I can, you have to catch it, you will catch it. Then try to cast the optimization sort of the problem formulation set such that, this is now, this is a sort of optimization problem set. I is equal to 1 to n, 1 over 2 pi, the exponential ui square, subjected means this has to be right on this surface. Gu is equal, this is right at the failure surface. So then this, you can rewrite that as okay, to maximize it, this portion, by maximizing this, this is the minus, so this will exponentially decay. So if you can, instead you can have this portion to minimize it. This is a maximizing problem set. Because this is a negative, exponential negative is keep going down. So I can reset the problem set saying that this portion is minimizing rather than the whole thing is maximizing. Make sense? So that's the next step to carry out. So this portion is now what we did, rewrite 1 over 2 pi n power exponential minus half, as I wrote down there, ui squared. So now we're going to deal with that portion to minimize it because of negative isn't right there. So this is equal to the norm of the u square. This is the square of each, the vector, each, the random variable square is equal to norm of the square. Okay? So now the problem is we're going to reduce it. Rather than maximizing, we're going to minimize this over square is the same thing, right? So problem is reducing or changing to the minimizing u subjected to g u is equal to 0. We try to reformulate the problem that we can handle nicely. My lips are getting dried up because it's desperate to try to convince you. So from here, what I can tell you, u is simply the distance, which is u1 squared plus u2 squared plus all the way through un squared. So this u norm is identical to not only beta, it's simply the distance from the origin to the point whose distance is really minimum, which is equal to the beta. Beta is called the reliability index. So that portions we did somehow Friday, but now get the final equation set to solve. So rewriting GU, once again, LU is equal to G. Now expansion point U star is MPP point. Right at MPP point, this G at MPP is equal to, if U star is MPP point, then this whole thing, this G function right at that point, G at U star is equal to 0, which means it's right at point here. So this you can set equal to 0, then you have a GU star and U minus U star T. I'm pretty sure you read all this over the weekend, right? Songtae, you read, right? Yeah, it's good. And I can claim that LU is equal to A naught plus I is equal to 1 through N AI UI. Then A naught and AI is nothing but when you multiply this and multiply that, simply speaking, just like that. Kyung-seok, take a look at. Then this is not direct multiplication like multiplying number. This is a vector multiplication and has to have a summation part is there. So A naught happened to be, right? So we did, this is a page 7 dash, page, not the equation 7-18, you will see that. 7-18, you see that expression. After you multiply out that, I is equal to 1 through N. This is what you have to eventually compute, but we're going to use example problem to get that, to understand details. A naught. A naught is like a constant term, and this has AI component in every direction. Okay, in every direction. And So if you look at this carefully, this is something like A1I plus well, AI plus Bj. If you have a two component in the vector, A is magnitude, B is magnitude in each directions. And if you say this is, see, two component, then you can compute the average or standard deviations or variances and all that. But in this situation, you have n different components in n different the random variable. So when you take the mean, then you have to take the mean of this component. Simply A plus B is a mean of C, for example. And if you gonna find the variance of C, then you have to have A squared plus B squared, vice versa, right? So this is A naught. And AI is multiplication of this guy to that guy, U. So if you do that, AI is del GU del UI evaluated at U star. That's it. That's AI. So now let's take the property of the L. So let's take first the mean. So mean of L if you take which is E times A naught, two terms of course, AI UI mean. If you take the mean of A naught, what's the result? A naught is a constant evaluated right at U naught. This is equal to simply A naught. If you apply the mean to the second term, what do you expect? Zero. Why is it zero? The mean of each component is equal to zero because the U space origin, mean starts right at the origin. So every component's mean is equal to zero. So this guy has to be, if you apply, this is equal to zero, this is only one. And second one is a little bit trickier. So now this is e to the e to the, by looking at this, L minus mu L squared. First term, you take away the mean. Each term, right? Each term you can deal with it. So mean subtract the mean here. This is the mean subtract the mean. So first term is equal to 0. But the second term, from second term, this is in UI means every component you have AI. Like A1 plus B1 plus C1, you take a standard deviation, then you have to take a standard deviation for each term. So that's what you have to do. So if you do that, this portion, so it's end up to have AI squared. Weird, isn't it? Every term, right? Origin is, the mean is equal to 0 because it starts at origin. And to get this, the variance, so you have to have each term square. Each random variable, each axis or has to be equal to 0. The sigma L, I can claim this is equal to the variance square for each component. By looking at this now, all the components are all spelled out. Then now finally you can get the result to compute the PF. That's the destination. So this is probability that linearized G function less than equal to 0 is equal to, in the U space, this is equal to the minus mu L over sigma L, which is really same as saying minus beta, reliability index. So this is equal to the phi, this portion, if I spell out, this is what you will end up to program to evaluate. Let's take a look at this is eventually what you have to evaluate. Back to original principle, evaluate the standard, the normal distribution function right at negative beta. Everything falls back into the original concept beta, and mu L happen to be this, which is A naught, and sigma L happen to be square root, because it's standard deviation, square evaluated at MPP point. So to solve this problem is again to find first MPP point, then evaluate this at the MPP point, then it's done. Then still, geez, how can I do that? So we have a 2D simple problem. We're gonna use that to get the whole process. And the whole thing, so now whole thing, oh, you know what? Yeah, just a minute. This is a minus term is there. This is minus term has to be here, right? This is right, minus here. It spells out that we can really evaluate the whole thing together. Is it correct now? It's a minus, and this is a minus, then cancels out, then eventually get down to 0, the plus. So doing this summation is inside this square root, but this summation is really open all here. So I'm going to take this guy, and this you put it together is a positive. So I can say that that is equal to the phi, which is summation I is equal to 1 through n del G U over del UI at U star, and the square root of the whole thing. Of course, this will be all like this. And I can put this guy even, I can put this in outside, because this square root is, everything is inside the square root in the denominator. So then I can close like that. So I'm going to say that this is this guy. I'm going to reset as alpha I. And by we write this is phi as a summation I is equal to 1 through n alpha I ui star. All this we have to evaluate. Correct? Alpha, So I'm going to put this guy, wait a minute. Kyuhan, say, wait. So here, I'm gonna say, how's that? I want you to reconfirm in your book, the Du's book, is all correct, except that you have to be careful on the pi and the square root of 2 pi. I put everything in the parentheses. If you want to take out outside of this guy, then I want to make sure this is n power. Otherwise, your calculation will be all different. Alpha I is all that. Okay, I think I'm gonna stop right here, and on Wednesday, I'm going to explain a little bit on the meaning of all this story, then getting into the MPP search. So U star search in the iterative fashion. Then after that, we're gonna do start with a simple example problem next Wednesday. Please read the text for all the detail. Please do. All right, so I'll stop right here.